Alright, so I did question number 39, which asks to explain why the sum of the imaginary part of the p distinct and the p root of any positive real number are always equal to 0. So the first thing that we need to start off with as kind of like a gut basis is that whenever something's to the pth power, whenever the degree is p, there will always be p roots. So take the example of x to the 5th equals 32. There we will actually have 5 roots. So the first root is the principal root, and that is the root 2 plus 0i. So obviously, as you can see in this part, the imaginary part is 0 already, the sum of the imaginaries. Now, the other roots of this are 0.62 plus or minus 1.9 I and minus 1.62 plus or minus 1.18 I. And because these are plus or minus, the imaginaries here and the imaginaries there will cancel out, which will make the sum of the imaginaries 0i plus 1.9i minus 1.9i plus 1.18i minus 1.18i equal to 0. So the sum is 0. But this will always be true because of the complex conjugate roots theorem, which states that for every time that a plus bi is a root, a minus bi will also be a root. And obviously you can have more than just a plus bi, so you could have like, I don't know, like c plus di, c minus di. But the point is, if you're talking about the imaginaries, you can kind of like cancel these out. These two terms will always cancel each other out, which will make the sum always equal to 0.